Okay, continuing our saga with the Nguyen-Wong B-tree. Today we are going to remove from the Nguyen-Wong B-tree. Now, last time we saw how to insert, and you notice in this figure in chapter A, that involved lifting a value up the tree. All right? What happens is you call the procedure, the insert procedure recursively, with that value as a parameter. And then when you get to the bottom of the tree, you insert it as in an empty tree at a leaf. Are you with me? And then when it got inserted at a leaf, then a node might have gotten too wide, and so you have to lift the value up the tree to go up as a result of inserting at a leaf. As everybody, you remember that strategy. That was the strategy of the insert algorithm. Now, however, what we're doing is we are removing from a tree. So what we have to do is, first of all, we don't know whether the value is going to be in the tree. If it's not in the, if we in the process of trying to remove the value, if it's not in the tree, we don't have to do anything. But once we find it, what do we have to do? We have to remove it. Here's going to be the strategy. What we are going to do is we're going to start at the top, and we are actually going to push a value down the tree. We're going to just start pushing from the top. We're going to start pushing a value down the tree. And on the way down, if we find the one that we want to remove, that's the one that we are going to continue pushing down the tree until we push it all the way down to what? Until we push it all the way down to the bottom, at which point, boom, it will disappear from the bottom, and then we will use our old same fix-up, all right, on the way up to repair any invariance that got violated on the way up. So it's kind of an interesting idea. We start by, because we don't know if it's going to be in the tree or not, right? But anyway, we're just going to push a value down, and then if we find it in the middle, that's the value. We will leave the one that we were pushing down there, and we will push the one that we found down all the way down to the bottom. And then when it gets to the bottom, we can remove it without violating any of the invariants. And then we'll just go back up and fix everything up on the way up. So now, on this figure, what happens is in part B of the figure, now what we're doing is we are pushing a value down the tree. As opposed to lifting a value up the tree, we are pushing a value down the tree. So now what's going to happen is we'll have this, and here again, it's in two steps. Like we saw, we combined these two steps in part A last time when we were doing insertion. But now with removal, what we're going to do is we're going to use the part B of the figure. We're going to be pushing a value down the tree. And so now it's going to be, instead of like combining split up and splice, we're going to be combining split down and collapse splice. Are you with me? So that's just the main idea of how removal is going to work. Okay, so let's just, and you will be amazed, it's remarkable how similar the code is, the structure of the algorithm is for removing comparing to inserting. So, so this will look very familiar. I think we'll be able to just based on knowing how to insert, I think it's not that big of a change to know how to remove. So look, okay, so it's the same as we had before. We have a remove and we have a rem helper. All right, before we had an insert, we had an insert helper. Here we have a remove and a rem helper. All right, and so the remove starts at the top of the whole tree, and then as before, the rem helper calls itself recursively, and you'll notice that the shape of the code is just very similar. It's quite nice. It's quite elegant. All right, so let's take a look at let's do a little code walkthrough. Oh, and by the way, it uses the exact same. Notice down here in the code, it uses the exact same, what is it to use for fix-up? What's our fix-up? Call what at the bottom? Split up and apply. It's the same one. Oh my goodness. You don't realize how neat this is. Okay, so let's do a little code walkthrough, and then we'll do some examples, and I think we'll be able to see how to remove. All right. And there are a few little surprises along the way. Okay, so check it out. Remove key order. So that's what the main program calls. So the order of the tree is the maximum number of elements in the tree, right? And then if the tree is empty, we just return. There's nothing to remove. So that's if the main tree is empty. Now look what we do. Look what we do right away. If the tree has one element, then we collapse the tree with its children. So now what we are doing is we are lowering the height of the tree by 1. But if we collapse the tree with, you understand what we mean by collapse the tree with its children? It's like, here, if it has one child, if this is like 50, and here, this is 20, 30, 40, and this is 60, 70, then collapsing this with the children is just this. 20, 30, 40, 50, 60, 70. You understand? So you see that maintains the balance and everything, right? Maintains the order, maintains the balance. The only thing that might not maintain is what? The what? The size. But that'll be fixed up on the way up because that's our we know how to fix that size. Remember, because look, what's our fix up? Split up and apply. And when does split up and apply execute? Only when what? Remember the split up and apply. Look at your code here on your paper. What's the first statement in split up and apply? If what? Size is greater than order. Size is greater than order. So when on the way back up, it'll fix that up. So let's see what happens then. If the tree has one element, collapse the tree with children. Now, and then call what? Rem helper, key, order, no op lambda command. That's just the same technique that we used before with insert, right? We call the helper with the no op lambda command for the function. Are we good? Okay. So now what does rem helper do? Now remember, what we are doing is we are trying to remove a value, and the strategy is we on our way down we will if it's in the tree on the way down we will find it. When we find it, we will continue to push it down all the way down. Are you with me? So when we get down to the bottom, if the tree is empty, that means that we haven't found it. That means it's not in the tree. So there's nothing to remove. Okay, that's the logic of that. We'll see how it works when we do a little run through of an example. So if the tree is empty, we return. There's nothing to remove. Else, if the tree has one element. Now, if the tree has one element, and if data sub 0 equals key, then what did we do? We found it on the way down, and we're all the way down here at the bottom. We found it on the way down, and it needs to be removed. So we can just do split down at 0. Now, do you remember at split down at 0, if it has one element that it removed it, it deleted it? Do you remember that? That's a little detail that we went over when we talked about the split down at method. If you go back and review that split down at method, what happens is if you split down at and it's just the size is 1, it deletes it. And I mentioned at the time that we're going to need this in the future, this behavior in the future. So you can go back and review that, but that's built into our split down at. Okay? So else, the key is not in the tree, and we execute command.host. So else, what do? We splice back up to the parent tree. See, otherwise what happened is we kept pushing one down, and we did not encounter the one to be removed, so we just kept pushing another one down, another one down, and when we got to the end, we pushed it down unnecessarily. So we just execute command.host. All right? So everybody, we'll do some examples here. But now look, else determine what? Now look, does the structure of this, is this coding idiom look familiar? Else determine k, the index, blah, 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 push data k down the tree, command gets, spice at k, call child, sub k, rem helper, command gets, command call. That's just almost identical to what we did before. Now there is one little thing though about this determine k There's one little thing about this determine k that's slightly different because we are pushing down, because we are pushing a value down. We're not just passing along a key value. We are physically pushing a value down the tree. So there's one little issue here that we have to be aware of. Let's suppose that this is 10, 30, 50, 70. And so the size of this is what? What's the size of this node? 4. So you understand this is data sub 0. This is data sub 1, sub 2, sub 3. Actually, let's make it one more. Let's have this be size equals 5, and let's put a 90 in here. Okay, is everybody with me on this? And this is child, what is this child? This is child sub what?
0.
Sub 0, and this is 1, and this is 1, 2, 3, 4, 5. Yeah? Now let's suppose that when we get down to this code where it says determine k, let's suppose here that the key, equals 40. Now my question is, based on that little pseudocode description, what's the value of k? It says determine k, the index for which data sub k equals key. Well, do any of these data equal key? No. Oh, so it doesn't. Or, if key is not in this tree, so key is not in this tree, okay? The index for which key is in the what? Left child of data sub k. So now, where would it be? It would be in the left child of, if key is 40, it would be in the left child of what?
2.
Of 50, which is at 2. So in this case, k would equal what? K would equal 2. Now, are you with me on that? Does everybody see that, how that works in that situation? And furthermore, if the key was 60, it would be what? 3, and so on and so on. Except there's this exception. It says what? It says parentheses, except when key is greater than data sub size minus 1. So how can that happen? That can happen if key is 100. Now if key is 100, then except when key is greater than data sub size, because size is 5, 5 minus 1 is 4, and key is greater than data sub 4. Are you with me? So in which case k gets what?
4.
Yes. In which case k gets 4. So what happens is, if key is 40, here's what happens. If key is 40, the 40 is between the 30 and the 50. What we are going to do is we're just going to arbitrarily push the 50 down. We're just going to push it down in preparation for finding the 40 somewhere else. But we can't push down something over here. There's nothing to push down. So if key is 100, we're going to push down 90. We're going to push down data sub 4. Are you with me? And you see why because what happens is that, because the next statement is what? Push underscore data sub k down the tree. Well, there is no data sub 5, right? So we have to push this one. Now, does everybody see how that works? Why that is? All right. So look, we push it down the tree with split down and then collapse. But this is the same code as before. Old command gets command gets spice at. So here, if it were 40, that command would get what? Spice at what? Here, if the key were 40, the command would get spice at 2, and we would pass spice at 2 down, just like we did before. And then we restore the old one and we fix it up on the way up, just like before. Oh my goodness, this is quite nice. Oh, and here, by the way, is what I mentioned a few minutes ago. The specification of split down at int I. If underscore data arrow size equals 1, the single value is deleted and this tree is empty. So there it is. I reproduced it for you here. That's the specification of split down at. Okay? That's why this comment, where it says split down at 0, that's the justification for the comment. Remove the key, this tree becomes empty. Are you with me on that? Okay, so that was... All right, now let's just do a few examples and then we'll see how this all works. Now look, so we're going to remove from an order, here again, we're going to remove from an order 4 Nguyen-Wong B-Tree. The root has only one, and then now let's say that the root has only one element. And so we will first collapse the root. Okay, so here we go. So here's our initial tree. Now, is it ordered? Yes. Is it balanced? Yes. Does it have the node restriction? Yes, because for an order 4, the atoms have to be what? Between what? How many data values in each node? What are the possible number of data values in each node in an order 4? 2, 3, or 4. 2, 3, or 4. And 2, 3. Oh, but what about the root? Oh, the root is the exception. So this is a good starting value. Satisfies all the restriction, so now what it says is remove 20, right? So here's our initial tree, remove 20. Okay, so that first statement in our pseudocode was collapse the tree with the children and call the helper with a no-op. So the 50 goes down between the 10, 20, 50, 70, 80 no-op. Right? Yeah? So this is just like part B of that figure, pushing down and, yeah? And notice that everything's maintained except for the possible size. And then what happens? Now, so let's go back and be looking at our code for rem helper. So what does it say? If the tree is the tree empty? It says if tree is empty. Is tree empty? No. It says else if tree has one element. Does tree have one element? No. So it says determine K, the index for which blah, 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 blah. So what's the value of K? If we want to remove 20, what's the value of K? Can you predict this? What's the value of K? It's 1. Good. It's 1. Determine K, the index for which the data value of K equals key. So so it is 1 because it's equal, not because it's the left of 20. Because it's 20. It's equal. All right. So and now what does it say? Push data what? Which is data sub 1. So what gets pushed down? 20. The 20. So the 20 gets pushed down. And notice that what gets passed along, the function that gets passed along, splice at 1. Right? Because if it were not equal, if we got pushed down and it were not equal, we'd have to splice it back. But this time, okay, splice at 1, and now it gets called again. Now what? Now, so let's go back to our rem helper. If the tree is empty, is this tree empty? No. Else, if the tree has one element, does it have one element? Does it have one element? Yes or no?
Yes.
Yes. So if data sub 0 equals key, does data sub 0 equal the key?
Yes.
Yes, because 20 in here is our key that got passed. So what does it do? Yeah, split down at 0, which we just saw before, does what? Removes the key. So that removes the key. So split down at 0, the tree becomes empty. Do not execute splice at 1 command. Right? Okay. Is everybody? Are we good here? And now what happens? One more thing has to happen. We go back. We go back up, and then what do we do?
It's like clean it up.
Well, yeah, but what is our cleanup? We go back up, and what's our?
Port 50.
No.
Yeah. Yes. We have to go back up and do our no. But we have to go up and do our no-op. Well, it's called split up and apply, right? But now, when does split up and apply execute? Only if the what? Only if it's too big. All right. So we call split up and apply with the no-op command, and there we are. Now, does everybody see that mechanism? All right. So one more. Let's do one more, or a couple more. So the next one is going to be removing from an order 4 Nguyen-Wong B-Tree. Here, what we're going to do is we're going to remove an element from a child. So we will push down an element from the root in anticipation of the deletion. So this is that strategy I was mentioning before. We are anticipating that we're going to delete, and we're going to just keep pushing down. And if we find it, the one that we got pushed down will just stay there, and then the one that we want to delete is going to keep going down and be deleted. Okay, so push down an element from the root in anticipation of the deletion. That's the strategy. So here's our initial tree. Here again, we have, it's a order 4, so anywhere 2, 3, or 4 data values per node. So we have 30, 60 through 10, 20, 40, 50, 70, 80 for the children. Is it ordered? Yes. Is it balanced? Yes. Does it have this node size restriction? Yes. Yeah? Are we good? Okay, now what does our code say? It says if the tree is empty, is the tree empty? No. So we call the helper, right? So here, we call the helper with the no-op command. Are you with me? Yeah? Call the no-op helper with no-op command. Now, if this tree, is this tree empty?
No.
No. Else if the tree has, does this tree have one element?
No.
No. Else what? Now determine k. So now what's k? Because our key is 20. So what's our k? 0. Good call. All right. So here it's 0, and so we go down. So we push 30 down, right? Now look, when we push 30 down, how do we do that? What does it do? It pushes it down and combines. Now here again, this is like your question from the other day. It's actually in 2 steps like we saw in that slide before. But now does everybody see how that got pushed down? Because if you push it down this way, the height, all the criterion are maintained of a B tree, of a balanced B tree. It's ordered. Every the leaves are all at the same level. Is everybody clear on this? Right? So we push 30 down. We call helper with splice at 0 command. Right? And so now what happens? So we go back. So is the tree empty? No. Does the tree have one element? No. So we determine k, the index. So now what is k? Now what's our k? 1 is correct. All right? So do you see what's going to happen? 1 is correct. So do you see what's going to happen? What's going to happen? It's going to push down the 20, because k is 1. It's going to push down the 20, right? So here. And so what happens is, so in part D of the figure, we push 20 down, right? And it's splice at 1. What gets passed along, the function that gets passed is splice at 1. But see, isn't this functional programming neat? You just pass down that function on the way. You make a new function, you pass it as a parameter, and there it is, ready to be executed at this level. Yeah? So we push the 20 down, we call the helper with splice at 1 command. Now what do? We go back and we do rem helper, key order, command, if the tree is empty. Is this tree empty? No. Else, if tree has one element, does it have one element? Yes. If data sub 0 equals key, does data 0 equal key? Yes. So what do? Boom. Split down at 0. The tree becomes empty. We do not execute the splice at 1 command. And now, tell me, on the way up, this says splice at 0. But what is our fix-up? It's call what? Split up and apply. Now, remember, how does split up and apply work? It only does something if what? If the what?
Greatest order.
If it's bigger than, are we safe here?
Yes.
We are, so it doesn't do anything. Do you see how that worked? It didn't have to, okay? So call split up and apply with the splice at 0 commands. It just stays the way it is. And then what? Split up and apply with no op, and boom, there we are. Is that slick? We can understand how this whole thing works. I considered showing you a mountain of pseudocode and ugly subscripts and if statements and while loops to show you how this is normally done, you know. Anyway, let's do one more. Now this is an interesting this is an interesting feature of the Nguyen-Wong B-Tree. It's actually possible. Look, if the element is not in the tree and you try to remove it, but it's not in the tree, it's possible that the tree will be modified. Are you with me? It's possible that the tree will actually be modified in the process of trying to remove a key that is not in the tree. Because what happens is it pushes stuff down in anticipation of, but then if it doesn't find it, the fix-up might change the tree. Now this is really interesting. So remove an element not on the tree with the root having only one element. Okay? the tree is modified to be, quote, better balanced in the process. So check this out. This is really neat. Here is part A of the figure. Here's our initial tree. So we have 60, and we have 10, 30, 40, 50 as the left child, and 70, 80 as the right child. Right? So that's our initial tree. And we want to remove 35. Now, where, is 35 in the tree? No. Okay, so what happens? So let's go to our top level. It says remove key tree. If the key tree is empty, is it empty? No. But it says else if tree has what? One element. So does tree have one element? Yes. So what do? Collapse it. Ha! Can you see what's going to happen? We collapse it with the no-op. All right? You call the helper with the no-op command. Yeah? And now what's going to happen? Determine k. So now what is that? What's our k? We're trying to do 35. So what's our k going to be? 0. What's k going to be?
2.
Is it going to be 2 or? Oh yes, it is going to be 2. Is that right? Because 0, 1, 2. Yes, it's going to be 2. So k is going to be 2. So what will it do? 0, 1. So what will it do? It will push what?
40 down.
It will push the 40 down. Yeah. So it'll push the 40 down. And the function will be what? Splice at 2. Now look, this is so cool. Splice at 2. All right? And so now it calls itself. If the tree is empty, the helper itself, if the tree is empty, is it empty? No. Else if tree has one element. Does it have one element? Yes. If data sub 0 equals its key, does data sub 0 equal the key? No. So it says else what? Key is on the tree. So what does it do? Execute what?
Splice at 2.
Command host. But what is command? Splice at 2. So it executes splice at 2 of the host. And the host is the one up there. So what does it do? It goes back up. Call split up and command with splice at 2. Oh, this is. But now what happens? We go back to our after the call of this one, and what does it say? Command gets the old command, so command gets no op. Now it says call split up and apply. But when does split up and apply execute? If it's what? If it's greater than. So what does it do? And now what does split up and apply do? It splits up at what? Size divided by 2. Is that right? So size is what? 1, 2, 3, 4, 5, 6, 7. Size divided by 2 is, what's 7 divided by 2? 3.5. The floor of that is 3. So what is it? So what is split up? 0, 1, 2, 3. So what goes up?
50.
Yes! Ha-ha! You guys are all on this. Call split up and apply with no op commands. 50 goes up. And look, do you see what our initial tree was? And now look what this is. After an unsuccessful delete, our tree is what? Better, quote, balanced. It has this feature of balancing itself better, even when you have an unsuccessful deletion. Is that neat? So as you go on and do insertions, like see before if you were to insert like a 35 in the original tree, it would have to do all the bunch of stuff. But here, if you insert 35 in this modified tree, it can go in there in that bottom thing without doing all that other stuff. So it actually keeps it. It has this neat feature of keeping the tree better balanced because of this characteristic. I think that might be. Oh no, here's another one. We got one more. Yeah. So we'll do one more, and then I think we'll have this one really down pat. So this is going to be removing from an order 4 Nguyen-Wong B-Tree. Now what we are going to do is we're going to remove an element that is not in the root or a leaf. So now we're going to pick up we're going to pick up the one to delete on the way down. Okay? Now, this is related, this note that I have initially is related to that question that I asked you the other day that we had to get straight. The question is, what is the height of tree A, B, C, and D in this next figure? See now, here is our initial tree, and we're going to remove 64. Now, do you understand that the height of tree A, can you tell what must the height of tree A be? 2. And then B, C, and D must each be what? 1. You see, because they represent trees, and the leaves all have to be at the same level. So does everybody see that that's the height of tree A, not shown is 2, the height of tree B, not shown is 1, C is 1, D is 1. So you understand that those actually go down. I just want to have to write all that stuff on the figure. Now, I think you guys, I think we're at the point where we can actually not even refer to the code, and we can just see how to do that K and deposit that function on the way up and see how this works. And if you're able to do this, you're able to do more than lots of other people who study the traditional B-tree deletions ever. This is quite remarkable. Check this out. So initial tree, remove 64. All right, so let's go to our code. So remove key, order. If tree is empty, is the tree empty? No, else if the tree has one element. Does the tree have one element? No, because it's 26 and 44. So we call the helper. All right, so the first thing that happens is, boom, we call the helper with the no-op. Now, does everybody see that? Are we good? Now look, what's the key? 64, right? So what is going to be our, now here, that's this. What's going to be our key?
It's going to be 1, sorry.
It's going to be 1. Are you with me? That's this situation. Does everybody see that? It's going to be 1. Our K is going to be 1. Good call. Very good call. And furthermore, what's it going to do? It's going to, that 44 is going to be pushed down. And so what will we, can you imagine what it's going to look like?
32, 38,
32, 38. Oh, wait a minute. Yes, 32, 38, 44, 52, 58, 64, right? It's going to go in between those. Does everybody see? Okay, so here. It's 32, 38, 44, 52, 58, 64. Notice that A is still good. The height of A and the height of B and the height of C and the height of D. Okay, that's all still, everything's maintained. And now it's 30. Okay, so now here, and furthermore, it was splice that 1. Why splice that 1? Because when we go up, we're going to splice that 1 on the way up. Because it belongs at 1, anything that goes up. All right, and so now what is K? 0, 1, 2, 3, 4. Yeah, yes, it is 5 because they are equal. So, is that right? 0, 1, 2, 3, 4, 5. Yes, it is 5. In this case, they are equal. So you're right. K is 5. So now what happens then? K is 5. So what's going to happen? What's going to happen to the 64? What's going to happen to data sub 5, that 64? What's it going to do? It's going to come down between the 60 and the 62 and the, sorry, it's going to come down between the 62 and the 68, and those will all be one big fat node. Does everybody see that? That's pretty simple. Right? And what got deposited there was what? Splice that, I mean the function that was spliced at 5. Why is that spliced at 5? Because when we come back up, it needs to be spliced at 5 in the parent tree to be fixed up on the way up. And now what's our K? 0, 1, 2. So now what happens? What goes down? The 64 goes down. So there's the 64 down. With what? Splice at 2. And now what happens?
Since it's 1.
Since it's 1, you push down, it gets deleted. With no, are you with me? Oh my goodness. And now what happens? Oh, you guys, it's amazing that you can follow this. Do you realize how many years I struggled and we never were able to learn how to delete from a B tree? It was too complicated. And now, here it is. This is amazing. Okay, so now what? Yeah, so splice it. Okay, so now what's the node restriction? It's too big, right?
Yeah.
So what's the size? 1, 2, 3, 4, 5, 6. 6 divided by 2 is what? 3. So data set 3 is what? 70. So what's going to happen? The 70 is going to go up and be spliced at what? 5. Spliced at 1 on the way up. Are you with me? Spliced at, sorry, splice at 5. Yes, I was looking, yeah, wrong. It's going to be, so splice at 5, so it's going to be, so this, wait, this, what was it? The 70 is going to be to the right of 58, and there will be 2 children, the 60, 62, and 68 on one side, and the 72 and the 74 on the other. Yeah? Is this good? Right? And now what happens? Is this node too big?
Yes.
Yes. So 1, 2, 3, 4, 5, 6. 6 divided by
Split up and
6 divided by 2 is what? 3. Data sub 3 is what? 1, 2, 0, 1, 2 is the 52. So what happens?
it's gonna go up.
The 52 go. Oh my goodness. The 52 goes up. And now what happens?
Nothing.
Well, we still have to do the no-op boom, but anyway, there it is. I tell you, this is the cat's meow. The fact that we can even do this, the fact that we can even know how to delete from a B tree is quite amazing. And here I give you the paper that Nguyen-Wong wrote. It's Design Patterns for Self-Balancing Trees. And here I think they presented it at an Object-Oriented Programming Systems, Languages, and Applications. It's a conference called UPSLA. And the thing is, this is kind of related to what are the 3 goals of this course? Yeah, C++, object-oriented design, and data structures. And what they did is, what they presented it was not at a data structures conference or an algorithms conference. It was at an object-oriented conference. So it like emphasized, it was at a conference that was specialized for object-oriented programming, and design patterns and stuff like that. And so I think it has not received the exposure, I think, that it needs to. And so I'm excited to present this on these iTunes U lectures. And here is it's on the website. You can access that, and there's the abstract. Anyway, this is the second balanced tree algorithm balanced tree data structure that we have studied. And what was the first one? What was the other balanced tree that we did?
B-tree. Oh, the left.
No, balanced.
Leaning.
Left-leaning what? Red, black tree. So the other ones that we looked at was the red, black tree. Now, what I'm showing you here in this slide is some common terminology. So if you Google this and if you research this stuff online, they don't use the terminology that Nguyen and Wong define in their paper for the order of a tree. They use slightly different terminology. All right? And so when you read the literature, you should be aware that a 2-3 tree in the literature is what we would refer to as a B tree of order 2. In other words, maximum of 2 data elements in a node. All right? So this is just some common terminology. So a 2-3 tree is a B tree of order 2. And the name comes from the fact that a non-empty node must have either 2 or 3 children. So you see, if it's an order 2, that means how many nodes? How many data values in the node? Either what? 1 or 2, which means either what? 2 children or 3 children. So they call it a 2-3 tree because of the number of children. Are you with me? So anyway, that's just a common terminology. Now look, any math majors in here? Isomorphism. You know isomorphisms? Yeah.
A one-to-one.
Yeah, a one-to-one correspondence, exactly. And so there is an isomorphism. There is an isomorphism between 2-3 trees and left-leaning red-black trees. And like you said, one-to-one correspondence. For every 2-3 tree, there is a unique left-leaning red-black tree. And for every left-leaning red-black tree, there is a unique what? 2-3 tree. All right? Now, watch this. This is really slick. This ties together these 2 different data structures that we've done. Now, check this out. Here is a figure of a left-leaning red-black tree. This is the one that we kind of, from previous slides, right, that we looked at. And now, we can verify that this is a left-leaning red-black tree, right? It's ordered, and remember, what was the deal with, by the way, tell me, what is the back height of this tree?
3, 4, 3, 3.
Good, it's 3. The back height is 3. right? Is everybody clear? Because when you count the black, when you go down to a nil, you don't count the red links. So the black height is 3. No matter which nil you go to from the root, it's 3, right? Now the existence of those red links means what? That the leaves are not all at the same level, right? The leaves are not all at the same level here. There's some are up, down, some are down. It's a little left leaning, so this is down over here and a little up over here, right? Okay? Now, what is a 2-3 tree? What is a B tree of order 2? They all have to be at the what?
Same level.
At the same level. So do you see how you can just, a one-to-one correspondence, do you see how you could actually convert this to a B tree of order 2?
Collapse all the red.
Yes! You just pull all the red ones up. So look, you see the red link from between 60 and 40? What you do is you pull the 40 up to be a what? In the same node of 4060 with 2 values. Is this mind-bending? And then what? Pull up the what? The 1020. So 10 would be a what? Would have 2 data values with the, yeah? And then pull up the what? The 12 with the 15? And then the 25 with the 30. So so how many data values? So you'd have a 4060, a 1020, a 1215, a 2535, and a 7580. And then if you did that and you pull them all up, what would happen to, because the black height? So all the leaves would be at the what? At the same. So look, boom. There it is. 1-to-1. Is that neat? Now answer me this. We saw that the left-leaning red-black tree was a special case that Sedgwick proposed for only allowing the red links to be on the left. What and how was that an advance over the general red-black tree? The general red-black tree allows what? Allows links on the right. So do you see that if you had a general red-black tree with links on the left as well as to the right, you could do the same thing. But now, because you could have a red link on the left and on the right, what would you do? The nodes could have what? 3. So it would be isomorphic to a what? To
order 3.
a B tree of order 3. Exactly. Look. So in the literature, these are called 2, 3, 4 trees. So what we call a B tree of order 3, which I think this definition of order is so much more easy to work with. But anyway, the literature defines the orders differently. And in the literature, when you see a 2, 3, 4 tree, that is a B tree of order 3. Nguyen-Wong defined the order to be the maximum number of data values in a node. So 2, 3, 4 trees. And the name comes from the fact that a non-empty node must have what? 2, 3, or 4 children. See? So 3 data up to 4 children. Are you with me? And look, here it is. There is general red-black trees. General red-black trees can have red links to the right as well as left. There is an isomorphism between 2, 3, 4 trees and general red-black trees. For every 2, 3, 4 tree, there is a what? A unique general red-black tree, and for every general red-black tree, there is a unique 2, 3, 4 tree. Yeah? And so probably in the manuscript I'll do a figure of this, but you can imagine what it would look like. Yeah. And in fact, if you look at Sedgwick's treatment, in his treatment of left-leaning red-black trees, he uses this analogy from the get-go. And so to follow his presentation, you kind of like have to know this. You have to know this isomorphism and but when we learned the principles of the left-leaning red-black tree, it was before we did B trees. So it's not necessary to know this, how B trees work, in order to understand red-black trees. But there is this very interesting isomorphism that's very well known in the data structures literature. Yeah? All right. Good deal. Are there any questions? Now, what's the deal with the homework? Is the homework due? Well, I'm kind of lost track. Tonight? You have an assignment due tonight? Are there any questions about that? Any?
Actually, I do.
Yeah.
Contains has a result of type int,
Yes.
boolean.
Yes.
So what do we return if it's not?
It's the -1.
-1.
You'd return -1 if it's not in there.
I just want to make sure that that's...
Right, right. Yes, it's not a boolean, because what, it returns the position. And if it returns the position in the node in which it is found, and if it's not found, it's -1. So, and if you look at the, I think if you look at the results of the unit test for contains, you'll see that that's how it gets printed out. Yeah. All right, good deal. See you next time.